Hello friends, welcome to my channel. Today we are going to discussing about mechanical vibrations. So before even going for mechanical vibrations, we need to learn some of the basics of mechanical vibrations. The basics of the mechanical vibration starts with complex numbers. Complex numbers. Complex numbers. If you have fair idea about the complex numbers, then you can able to solve any of the problem in the complex numbers domain. And one of the and we are also discuss about Lagrangian mechanics. Lagrangian mechanics. In the Lagrangian mechanics, you might heard of Newtonian mechanics. But the problem with the Newtonian mechanics is that Newtonian mechanics involves great form of constraints. For example, if you take a simple pendulum problem like this, if this is a mass, when you are going to write free body diagram for this particular mass, when you are going to write free body diagram like this, what happens is that you're going to take a coordinate system over here like this, and you have a tension over here T, and you resolve it this theta into two ways. One is called as T cos theta in the horizontal direction, and another is the T sin theta in the vertical direction. When these things happens is that what happens also that this T cos theta is also equated to this mass is equal to x double dot is equal to T cos theta, and m is equal to y double dot is equal to T sin theta. So in the horizontal direction you might see that there is no forces over here, but in the vertical direction you might find that minus mg is the force which is available over there. So therefore, see, observe this equation, T sin theta minus mg is equal to m into y double dot. So how many equations you got? You got one equation, you got two equations over here. So for simple problem for this particular, to apply the Newtonian mechanics also, you will find that that you have to apply two equations. And see this tension is coming inside the formulation, which makes that very difficult for handling this type of problem. The best way to solve these types of problems, especially in the mechanical vibration, is using the Lagrangian mechanics. Don't get freaked out by this Lagrangian mechanics. I will make so many problems in this particular class that you will start feeling very comfortable about this subject. So the Lagrangian mechanics involves that you have to derive one function called as L function, and you have to differentiate that function plus some reaction function, and then dou L by dou x is equal to 0. This is called as the Lagrangian equation. All is L is equal to sum of the kinetic energy minus sum of the potential energy. That's all. You have to develop this Lagrangian function, and if you develop a Lagrangian function, all you have to do is differentiation. Once you got the differentiation, what you ended up is something which is called as the equation of motion. So to derive this equation of a motion, see this equation of motion, mx double dot is equal to T cos theta, and see this T sin theta minus mg is equal to my double dot. You got two equation of motion for one single particle, but for a simple Lagrangian mechanics you can able to solve this like a very easy way. So let's all see some problems which you start feeling little comfortable about it, and I'll make it very comfortable for you. So how does this Lagrangian mechanics goes with us? Let's take a paper and is there any paper left? No. I'll take a paper for you. Just stay with me. See, this Lagrangian mechanics, I'll make it easy for you, don't worry. See this particular pendulum. I'll make a pendulum for you. See this particular pendulum of mass m. Okay, and it has a theta over here. Okay, so this particular pendulum is going in this way, theta. So identifying that single coordinate is enough for this particular pendulum to find the natural frequency of a system. So what you have to do is that since it goes in this way, and this is tension in the string will be there, this has to be a massless string. Okay, see the magic how it happens. What will be the potential energy of this particular mass? This is the length of the pendulum over here, and as it goes over here, so it will be L minus L cos theta. Okay, it will be L minus L cos theta. If it is L minus L cos theta, what will the potential energy? Potential energy is equal to V, that is equal to m into g into h. H is what over here? M into g L minus L cos theta. So simply mg L 1 minus cos theta. Okay, now what is the kinetic energy? Kinetic energy is nothing but, see, this mass is rotating like this. Since it is mass is rotating like this, what it has to do is that it has to rotate. So it has a rotational kinetic energy, half I into theta dot square. Okay, now what is this? This is L. Now what is our Lagrangian function over here? L is equal to T minus V. L is equal to half I theta dot square minus m into g into L 1 minus cos theta. Okay, this is our Lagrangian function over here. So this is the Lagrangian function, and what we have to do is that we have to write the Lagrangian equation first. What is the Lagrangian equation? Dou by dou t, dou L by dou x dot theta dot minus, since there is no reactive forces, all you have to do is dou L by theta is equal to 0. Okay, let's solve this. Dou by dou theta of L, what it means? Differentiate this functioning, we get half into 2 into I theta dot and I into theta dot. That's all. Now what happens if I differentiate with respect to time? D by dt of this entire dl by d theta, what you get is I into theta double dot. This is 1. And see this, differentiating with respect to theta, what we get over here is that dou L by dou theta is equal to minus mg minus mg. D by dx of cos theta is what? D by dx of cos theta is minus sin theta, L minus sin theta. So this will become plus over here, because this becomes minus over here. So substitute in this equation, just substitute in this equation. What you will get? This is the part of the equation, this is the part of the equation. Just write this over here, theta double dot minus of what is dou L by dou theta minus mg L sin theta is equal to 0, and see I is equal to theta double dot plus mg L sin theta is equal to 0. Now for small angle sin theta is approximately is equal to theta, so I into theta double dot plus mg L theta is equal to 0. Now see the magic, theta double dot plus mg L by I is equal to 0. This is what this is the equation of motion for this particular pendulum. See, for this particular pendulum, if you go for a Newtonian mechanics case, you have to find two different types of differential equations, but if you go for a Lagrangian mechanics case, it becomes so easy that you will end up with only one variable. These types of variables are called as generalized coordinate system. It means that the number of small variables that are required to define the system. For me, though theta is simple, okay, theta is simple enough for us. It is will be very stupid for any person to take two different form of motion for one single particle. Okay, so this is the equation of motion, and this is the paper one. I'll write 2. Okay, so what happens is that in the 3, finally we got theta double dot plus m into g into l by I, theta is equal to 0. I is equal to m l square, because this particular pendulum of mass is rotating. So I is equal to mr square. Over here in our case is L. I is equal to ml square. So substituting theta plus mgl by ml square of theta is equal to 0. Mass cancel, ll cancel. Theta double dot is equal to g by l is equal to, sorry, of theta is equal to 0. The natural frequency of the system is g by l. Omega n is equal to g by l. G by l, square root of g by l. This is the natural frequency. Omega is equal to square root of g by l. This is the natural frequency of the system. See how easy it is if we have selected the Lagrangian mechanics. This particular one equation have solved so many problems for us. Okay, I will take one more problem and let me help you with some more problems. Okay, let's see. Study. Okay, I got papers. Let's go. The second problem that we are going to deal is in mechanical equation. In mechanical domain, you might have seen this type of sorry, I'm so sorry for that. You have seen this type of spring, and this is the mass m, and this is k. Deriving equation for this particular stuff is much more easier in the using Lagrangian mechanics. Okay, if this is the mass, okay, if this is going the if this is the let's call it as q. Okay, if this is the direction of the motion, or if you are comfortable, I can make diagram easy for you by y. Okay, if this is the direction it is going over there, so this is a constant k. Now simply, what is the kinetic energy? T. Since this is only mass, what it only has is that half into m into y dot square. That's all. And what is the potential energy of the spring? See, the spring in this side is over here is 0. Only it has a deflection over here. The potential energy of the spring over here is half into k into y square. That's all. Now Lagrangian function for us is t minus v. What is t minus v? Half m y dot minus half k y square. That's all. We have developed Lagrangian function. What we have to do next is that we have to substitute this equation in our Lagrangian equation. Dou L by dou y dot minus dou L by dou y is equal to 0. Okay, what will be the dou L by dou y dot? See over here, I will show you. Dou L by dou y dot is equal to, y dot is only over here, it will be a square, so it will be m y dot. What will be dou by dou t of dou L by dou y t is equal to m into y double dot. Okay, next, what will be the functions over here with respect to dou L by dou y? Though with respect to dou L by dou y, dou L by dou y, see this is the Lagrangian function. If you differentiate it, what will happen? Minus half into k into 2 into y and further ky, because this 2 and 2 will get cancelled. Now substitute in this Lagrangian equation dou by dou t into dou L by dou y dot minus dou L by dou y is equal to 0. Substitute this over here, minus of minus ky. Substitute my double dot over here. That's all, equal to 0. My double dot plus ky is equal to 0. Y double dot plus equal to k by m. Dividing this entire equation by m, you get this one. Y double dot plus omega n square of y is equal to 0. That's all. This is the equation of motion. This is the equation of motion for this system. Yeah, in many books it might confuse you, but if you use this Lagrangian mechanics, if you develop this Lagrangian function and use this Lagrangian mechanics, things will be very, very comfortable for you, I am sure. Okay, this is paper number 4. Let's do one more problem. Okay, this is 5. Now this time, in most of the mechanical engineering, you might have seen that this type of mass over here. Now over here also, this is the y direction. And how you will solve this problem? If this is k, this is c, simple. What is the potential energy? Half k y square. What is the kinetic energy? Half m y dot square for this function. What is the resistance function? Resisting function is half c x dot square, y dot square, because this damper acts as a resisting function. Now see how it is happening. Just you have to apply in this Lagrangian function. Now what is our Lagrangian function? L is equal to t minus u. What is t over here? Half m y dot square minus what is potential function? Half k y square. Okay, now after this, just differentiate with respect to y dot. You will get m y dot, and dou L by dou y you get minus ky. Okay, and simply you have to substitute in this equation, that is dou L by dou x dot dou by dou t plus dou r by dou x dot dou y dot minus dou L by dou y is equal to 0. Okay, now what happens is that simply by putting this over here, what you will get is that dou by dou t of m into y dot plus what is the differentiation of this particular function? You will get c into y dot and minus of what is differentiation over here? Minus ky is equal to 0. So you will get my double dot plus cy dot plus ky is equal to 0. Okay, so this is how it is. It is very simple. Lagrangian mechanics will save you lot of time. Okay, see, Newtonian mechanics are good, but Newton mechanics is mostly helpful in static problems. If things are very static, okay, Newtonian mechanics will will do so much good for you. But things such as these equations, like these systems which are moving, you have to use the Lagrangian mechanics. The reason behind this particular Lagrangian mechanics is that if you take a simple cart problem also, if you take a simple cart problem, okay, if you take simple cart problem, when you do a free body diagram for this, what happens is that you get a RA and you get a RB. Okay, once you got RA and RB, what happens is that this RA plus RB is equal to M. This reaction forces comes into picture. In order to solve this, eliminate this problem of this reaction forces, even though you see this, even you take a very simple pendulum. By now you might have seen that this particular pendulum goes like this, and what happens is that since the tension over here, which is also acting over here, which is perpendicular, this particular tension is doing no work, because work is equal to Fs cos theta. If work is Fs cos theta, if Fs, if cos 90 degrees, see this is 90 degrees tension, and this is whatever small displacement you take, it becomes 0. The work done by this particular mass or this particular tension in this particular system is, what happening is that it is doing 0 work. If it is doing 0 work, then what is the use of it? See, even though in this Newtonian mechanics also, this reaction A and reaction B is doing 0 work. It is not doing any work. Since it is not doing any work, then what is the use of it? So idea is that to use the minimum amount of variables to define the system of equation. See this mass over here, it will go in this way, x is this direction. Okay, and that's all. This is for mechanical vibration. I will do something which is related to civil engineering right now. Okay, doing something for civil engineers also. I see that most of the people get confused in engineering mechanics, so let's speak some about engineering mechanics. See, one of the engineering mechanics, what with the equilibrium equations plays a key role. Equations plays key role. Okay, what equilibrium plays a key role? First is sigma f of x is equal to 0, then sigma f of y is equal to 0, and also m, sum of m is equal to 0. These are the only 3 equations available to solve problems in the statics. Okay, there is no such beyond this thing. Only beyond this thing is that if you go 3 dimension, you will get a f of z is equal to 0 as one more. And if you go 3 dimension, you will also get 3 more equation, that is sum of the moment about the x is equal to 0, sum of the moment about the y axis is equal to 0, sum of the moments about the z axis is also 0. Okay, and we will also get to some more. F of x is equal to 0, sigma f of y is equal to 0, sigma f of z is equal to 0. Because since body is in equilibrium, even if you take a small roller or like this, the body is in equilibrium, the weight is over here, the body is in equilibrium, it is not doing any work. Since it is not doing any work, what happens is that since it is not doing any work and it is just like that over there, it is static. So these are the equilibrium equations that you have to use to solve a problem. I'll solve one problem for you right now, and let's go from there. Most of the civil engineering people are very confused about the beams. So I will draw one simple beam and let me take some examples like this. So this is the weight W and this is the weight RA and this is the RB. Now see, in this particular case what happens is that apply sigma f of y is equal to 0. What you get is RA is going up plus RB, and this W is coming down, minus W is equal to 0. RA plus RB is equal to W. Okay, W. Now how you will find what is RA and what is RB? This is a question mark. Now you need a length, and this is L by 2 and this is L by 2. Okay, half of the beam. Now sum of the moments is equal to 0, right? I have discussed. So take moment about A. From A you have to take the moment. RB is going in upward direction, so RB into L. W is going in downward direction, W into L by 2 is equal to 0. So RB is equal to RB into L is equal to WL by 2. This L get cancelled. RB is equal to W by 2. Substituting this equation in the one, so let it be 2. Substitute 2 in 1, we get RA is equal to W minus W by 2 is also W by 2. That's all. Easy reactions and easy peasy. So RA is equal to W by 2 and RB is equal to W by 2. Okay, let's solve one more problem. Okay, the second problem is what we are going to discuss is same beam with UDL load. Okay, most of the reactions will be, this will be pin joint and this will be the roller joint and this is W. So what we have to do for this particular beam is that we have to draw free body diagram for this. Replace this particular roller support with RA. Suppose this is A and this is B. Replace this pin roller support with one RB. Sorry, this is a pin support and this is a roller support, and replace it with by load. Now after doing this, what you have to do, apply sum of f of y is equal to 0. RA is going up, RA, what else is going? RB is also going up, and what is coming down? Minus W into L. W into whole is equal to 0. RA plus RB W into L is equal to 0. RA plus RB is equal to W into L. Okay, now once we have got this RA into RB is equal to L, what we can do is that taking moment about A, you have to take moment about A. Sum of the moments about A is equal to 0. So RB, what is the length? This is the length. RB into L minus W into L. Okay, RB into L, W into L, and where this load is acting? Right at the center, L by 2. So RB, so this is equal to 0. RB you will get something which is W L by 2. Okay, this is W L by 2. Similarly, because the beam is symmetric, RA is equal to RB. You can also substitute RB in this particular equation 1 and solve this problem. Okay, let's go further. Let's go further. Let us take cantilever beam. Okay, cantilever beam with a UDL load. See, this is a cantilever beam. Okay, most of the civil engineering, mechanical engineering people are familiar with it. So, what is the free body diagram for this? Free body diagram. Free body diagram is this is the beam. What you get over here is the load, that is the reaction at A, and this is B, R A, and you also get a moment over here, M A. Okay, now this is W. Now writing the equilibrium equation, sigma f of y is equal to 0. R A is going up. What is coming down? This load is coming down. Minus W into what is the length of the beam? W into L is equal to 0. RA is equal to W into L, that is WL. That is the reaction over here. What is the moment reaction? Sum of the moment is equal to 0. Sum of the moment is equal to 0. What you get is, if you take moment from here, W into L into L by 2 minus MA is equal to 0. So MA is equal to W into L square by 2. So these are the final equation. RA is equal to W into L, comma, MA is equal to W into L square by 2. Finally we got the equation. Now we can go further to calculate the deflection of this beam also. See, the deflection of the beam is very simple. See, most of the people got confusion over here. How they take the deflection. Okay, let this be x is equal to 0, x is equal to L. Now if we make this particular section, okay, make this particular section, and this is the distance of x. Now what you have to do is that if you cut a section like this, okay, and this is the moment, okay, now this is the vertical force and this is the M. What is the reaction? The reaction is W L by L square by 2. What is the reaction over here? That is W into L. Okay, that is the W into L. Now how you will write the moment equation? Mx. Now this load is going down. See, this load is going down, minus W into x square by 2, and this is also following it, plus W L square by 2 is equal to 0. Mx is equal to W minus W L square by 2 plus W x square by 2. This is 1. Now we have got this particular equation. E into I into y double dash is equal to m of x. If you do this differential equation, you will end up something which is like this, minus w x power 4 by 24 something with deflection. I will not do this deflection because teaching small things is very important than teaching large things first. Okay, if you want, you can interested, you can do. Okay, let's draw the bending moment diagram. See how you will draw the bending moment diagram. See this equation. What is this equation? This is a parabola. This is parabola, my dears. These are parabola. So if this is the equation and this is the load, this is what? This is the parabola. It's a parabola. So you will end up something like this. Parabola. And what will be over here? Minus W into L square by 2 parabola. Secondly, if we have a point load, okay, how I will draw for this? Simple. Take a section from here. Okay, take a section from here, cut the beam like this, replace it with the moment m of x, or and okay, before going over here I have to find reactions of this beam. I'll do it freshly. Okay, see this beam, this is having one load over here, W. Now what is the free body diagram for this? Free body diagram is something like this. You have a M at A and this is W. Okay, this is the length L. RA is going up minus W is equal to 0. So RA is equal to W. What is the moment reaction? Sum of the moments is equal to 0. So MA plus W into L is equal to 0. MA is equal to minus W into L. So this beam have a reaction over here which is positive W, and it has a negative reaction over here, that is minus WL. Okay, now how you will write the deflection equation for this? Just simply come over here and then take a section this beam W mx. Okay, now after sectioning this beam, what are the reactions over here? This is W and this is what? Minus W into L. Okay, and this is what? This is mx. So mx minus, because you have done section at a distance of x, so W into x, and this is what? This is minus moment, minus W into L is equal to 0. So mx is equal to Wx plus WL. So this is the equation. Double integration will give you W x cube by 3 plus WL into x plus A, Wx power 4 by 12 plus Wx square by 2 plus Ax plus B. Solving for y of x, you will get this equation. Okay, see, solving these problems are easy once you understand this concept. Okay, so let's do some more problems on engineering mechanics. Okay, so that is beams, that is for the reference, and that's all. Let's see resolution of forces concept. Resolution of forces. See, resolution of forces means if you have a coordinate system like this, and this is the theta. So the horizontal component of this particular is F cos theta. Similarly, the vertical component over here is the F sin theta. This particular component is parallel over here, so we mostly project this particular over here. So a force is revolved in F cos theta and f sine theta like this. Okay, this and this are both same. Simply we have resolved these components over here. If we have a multiple forces, okay, if we have a multiple forces, what happens is that um, if we have multiple forces like F1 and F2 like this, then what you have, this is theta 1 and this is theta 2. So what you can do is that sum of the horizontal forces, or sum of the f of x is equal to 0, you will get f1 cos theta 1 plus f2 sin theta 2 is equal to 0. And similarly, vertical forces will be f1 sin theta 1 plus f2 sin theta 2 is equal to 0. These are the vertical forces. Okay, so this is called as the resolution of forces in a plane. See, this particular paper is a plane. Okay, so what we did is that we have resolved the force F and we into two components. One is F sin theta, one you might also remember in the trigonometry also that if this is the theta, the horizontal component sin theta is equal to opposite sides by hypotenuse, and cos theta is equal to adjacent side by hypotenuse. Okay, adjacent side by hypotenuse. So what is our hypotenuse? Our hypotenuse is force. So we are finding what is this and we are finding what is this. Therefore, so opposite force is by F, ADJ by F. What this F is done is it came over here. That's what it has happened. This is nothing but the opposite force. Okay, see, it will be easy once you understand the resolution of forces, and once you have done this, let's take three problems and solve it. Okay, let's take this one. This is f1, this is f2, and this is f3. Okay, and this is theta 1, theta 2, theta 3. Now sum of f of x is equal to 0. What you will get? F1 cos theta 1 plus f2 sin cos theta 2 plus f3 sin theta 3 is equal to 0. Why we are using 0? Because it's a static problem. Nothing is moving. Forces are there. All civil engineering problems are static problems only. There is no dynamic problem unless you go for some building analysis, for vibration analysis of the building, vibration analysis of a structure. Until unless you don't go for a vibration analysis of a structure, you will not find any form of dynamic equations for in civil engineering. Most of the civil engineering are static, and that can be easily done by this particular static equilibrium equation. So this is f of x is equal to 0, then f of y is equal to 0. Let's check. F1 sine theta 1 plus f2 sine theta 2 plus f3 sine theta 3 is equal to 0. Okay, so these are the two equations which are very important for us, and that's all. These are the two equations for this particular. What if you get a force like this? This is an F1 and this is an F2. Okay, and this is theta and this is theta 2. Theta 1 and theta. How we will write force for this? Simple. Since it is the first quadrant, this will be F1. Okay, sum of f of x is equal to 0. Since it is the first quadrant, f1 in the first quadrant is f1 cos theta 1, and this is f2 which is in the second quadrant. So you know that the sign changes as you go from this origin. It will go minus. So minus f2 cos theta 2 is equal to 0. How will be the vertical forces? Sigma f of y is equal to 0 is f1 sine theta 1. This particular force is, see, this particular force is projected on this, and this particular force is projected on this, so both will add. f2 sine theta 2 is equal to 0. So this is are the two equations which we have developed from the engineering mechanics point of view. Okay, in equilibrium equation, understand that these two will produce one resultant. So there was some resultant. The resultant force is square root of sigma f of x whole square plus sigma f of y whole square, and the angle between them is tan theta is equal to f sigma f of y divided by sigma f of x. Theta is equal to tan inverse sigma f of y by sigma f of x. Okay, theta is equal to tan inverse, so that you will get a resultant like this combination of two forces, because these two forces follows the parallelogram law of vector gram law of vector. Okay, if you don't know parallelogram law of vector, I'll write for you, don't worry. If two p and q are two sides of the parallelogram and their angle between them is theta, the resultant is r square is equal to p square plus q square minus 2pq cos theta. This is the uh, parallelogram law. Okay, there is something which is also called as sine law or cosine law. If forces are like this, if f1 f2 and this is f3 and this is theta 1, this is theta 2, this is theta 3, so f1 and the opposite is cos theta 1, f2 opposite is theta 3 cos theta 3, f3 opposite is what, cos theta 2. This is another cosine law. Cosine law. Okay, so yeah, let's take a break. It's almost 50 minutes and I'll resume back at I'll resume class at 10:30. Okay, let me write this. Resume at Hi guys, thank you for being with me. Let's resume our explanation. Okay, okay, let's go. Yeah, till now what we have discussed in uh, in this particular subject, which is till now what we have discussed over here is that uh, we have started with something which is number one, mechanical vibration. Mechanical vibrations and continued our discussion on strength of materials and basics of engineering mechanics. Okay, we have started with Lagrangian mechanics. Okay, and we have explored one equation like this. In most of the textbooks, you will find this equation as this is qi dot. Okay, I'll write again. Dot. I is called as number of masses. Yeah. See, if you have three masses, you will get three equation of motion. Okay, this is as simple as that. If we have three masses, we'll get three equations of motion. Okay, let's take some problems, solve it. Okay, let's take one problem and solve it. I am coming to just taking out a problem. Okay, got it. Okay, this is a problem. K1, K2, this is a problem for us. How you will solve this particular problem? Simple. This is Q1. These are the two motions for the masses. So, what is the potential kinetic energy for this mass? dot square, half into q2 dot square. How many springs are there? 1, 2, 3. 3 springs are there. Springs are there. For this one, I will write half k1 q1 square. For this spring, half k2 q1 square minus q2 square. Okay, or you can write as q1 minus q2, half k3 for this spring is what? q3, there is only q2, right? q2 square. That's all. Let's rewrite this. Half k1 q1 square, half k2 q2 minus q1 whole square plus half into k3 q2 square. What is our Lagrangian function? L is equal to t minus v is the Lagrangian function. Then how you will write? T is this one. Are you able to see? T minus v is equal to half m1 q1 dot square plus half m2 q2 dot square minus half into k1 q1 square plus half into q2 minus q1 square into k is k2, right? Plus half into k3 q2 square. So this is our equation. And what we have to do? We have to apply partial differential equation for our Lagrangian function. Okay, for our Lagrangian function. So see, there are two masses. So you have to what? You will get two equations of motions. Since you have two masses, you will have two equations